we're starting Unit 6 today, which is polynomial functions, and 6.1 is characteristics of the equations of polynomial functions. That's on pages 384 to 397 in your text. Our curriculum outcome is to demonstrate understanding of the representation and analysis of data using polynomial functions of degree less than or equal to 3, and that's what we're doing today. Logarithmic functions, exponential functions, and sinusoidal functions. And lesson objectives, number 1, to be able to determine the end behavior of a polynomial function. And number 2, to be able to determine the number of possible turning points and the number of possible x-intercepts by looking at the equation of a function. So when looking at polynomial functions, we're going to be focusing on 3 types of functions. The first one is linear functions, and those have a degree of 1, which just means the highest exponent in there is 1. And the standard form for a linear function is f of x equals ax plus b. You just have an x term and a constant. Quadratic functions that we've talked about a lot in the past have a degree of 2, which means there's an x squared in there. And the standard form for those are f of x equals ax squared plus bx plus c. And our third type are cubic functions, and those have a degree of 3. And so your standard form there is f of x equals ax cubed plus bx squared plus cx plus d. We're also going to be focusing on the following characteristics of polynomials by examining the shapes of these 3 functions. And we're going to be looking at possible number of x-intercepts, the end behavior, which is new, possible number of turning points, which is also new, the domain, which is an old topic, and the range, which is also an old topic. So here we are, we're in Desmos graphing calculator at desmos.com, and we're going to look at these functions and take a look at those characteristics we were just talking about. So the first one are linear functions. So this is the function of x plus 2. You can see that there's one possible x-intercept, because it's just a straight line. Linear functions always have the concept that there's only going to be one x-intercept. The domain of this thing, well, lines go on forever, so the domain is going to be xer. It's all the real numbers. And the range in this case is going to be yer, because it's also all the real numbers. Now, in the text, you may see it written like this, x with a line, and then xer, and then y with a line, and then yer. In other textbooks, this may not be a line, it might be a colon. So that's just the way that we write the domain and the range of functions. So we've looked at domain, range, possible x-intercepts. There are no turning points in this graph. A turning point is where a graph will turn from going up to going down, and a line is linear, so there's no turning points. But the important thing we're going to look at is this, the end behavior of this function. So the end behavior of this function, it looks like it starts in quadrant 3 down here, and it ends up in quadrant 1. And so we read it like a book. We go from left to right. So we start on the left-hand side, we end on the right-hand side. And this is x plus 2. If we also graph 3x minus 2, it's still starting in the third quadrant and finishing in the first quadrant. Now, if we graph negative 3x plus 4, that's changed now. Now we're starting in quadrant 2, and we're ending up in quadrant 4. And the only thing that's changed between these functions is the fact that we no longer have a positive value in front, we have a negative value in front. So this, what we call the leading coefficient, is really, really important. It determines what quadrant the function starts in and what quadrant the function ends in, and that's called the end behavior. So the leading coefficient, and in this case for negative 3x plus 4, that would be the negative 3. And in the previous cases, 3x minus 2, that would be a positive 3. So the leading coefficient tells you which quadrant they're going to end up in and which quadrant they're going to start in. So again, if it's positive for a linear function, it starts in 3, ends up in 1. But if it's negative for a linear function, it starts in 2 and ends up in 4. And just to illustrate that point, I have put in one more line, negative 2x plus 9. I might have to zoom out a bit. And you can see that it also starts in 2 and ends up in 4. So now we're going to take a look at our quadratic functions. So first I'm going to graph 2x squared plus 4x. And we see a parabola, which we've dealt with a lot before. So we know that in a parabola there's 2 possible x-intercepts. It doesn't necessarily have to be any x-intercepts, because that parabola could look something like this, or something like this, so it actually never crosses that x-axis. Or there could be one x-intercept, because it could come down and touch it and then go back up. So we know that there's a maximal possibility of 2 x-intercepts here. So we also have 0.5x squared minus 4, and again showing you that possible 2 x-intercepts. Now let's take a look at the domains. Again, the domain is pretty easy for parabolas, because it's always going to be xer. Because we go all the way from left to right, this function keeps on going forever. The domain changes a bit though. Your domain can be, y can be greater than a number, like in this case, y is greater than, say it looks like about -2. So you could say y is greater than -2. And for both of these functions, it's a y is greater than -2 sort of thing. Now in the text and in any other text, you might see it y with the vertical line, y is greater than -2, and then they're going to say yer, which just means it's all the real numbers that are greater than -2. So what happens if we throw a negative in front of this x squared, because both these values are positive? Well, what happens when we throw a negative in is that, once again, it's going to change our end behavior. So when it was a positive x squared, it started in 2 and ended in 1 for both the red and the blue functions. But now that it's a negative x squared, it's starting in 3 and ending up in 4. And we're going to graph one more just to confirm. Negative 0.25x squared minus 0.4x plus 16. And again, starting in quadrant 3, ending up in quadrant 4. Now, looking at turning points for parabolas, it looks like there's only going to ever be one turning point, and that's at what we call the vertex. And that's because it goes from, if we look at the red graph, it's decreasing, it's going downwards, and then it hits its turning point, and then it starts going upwards. The black graph, it's opposite, it's increasing, hits a turning point, and now it's decreasing. So we're looking at our cubic functions, and we've never seen cubic functions before, but the basic cubic function is just x cubed. And here's what x cubed looks like. It's starting in quadrant 3, it's ending up in quadrant 1, and it looks like there's a little change in the graph here. So it's not quite a linear function, it changes a bit. So what happens then if we just throw some numbers in for a, b, c, and d? If we look at 4x cubed plus 5x squared minus 3x minus 6, you can see the green function now. It's increasing, and here we have a turning point, and now it's decreasing, and then we have another turning point, and then it's increasing again. But if we look at the end behavior, we're still starting in 3, ending up in 1. Now, we happen to have 2 turning points here, so whenever we have a cubic function, there's a possibility of 2 turning points, even though with this first one, with x cubed, the blue function, there wasn't any turning points. It was just kind of a jag in the line there. So, the next thing is that we can also find out how many x-intercepts there are. Well, if the function does look like this, which x cubed functions can look like, we know that there could be a maximum of 3 different x-intercepts, 1, 2, or 3. Now, you could have 1 x-intercept like we have with the green function and the blue function. They both only have 1 intercept, or it could be as little as 2 intercepts. And the 2 intercepts would look something like this. So if we had a function here, there's 1, it comes up and touches, and then it goes down, and then it passes through after. So we've got our x-intercepts covered. Now our domain, again, it's really easy because it's everything from left to right. And our range is also very easy. So our domain is xer. And our range is also going to be yer this time because this function always continues downwards all the way and always continues upwards all the way. And finally, the last thing we're going to look at is what happens if we change that value in front, that leading coefficient again. So if it's a negative cubed graph, then we've got a change in where it starts. It starts in quadrant 2 and it ends up in quadrant 4, but we still have 2 turning points here, and we still have 3 x-intercepts. So a couple examples to finish off the lesson. It says, sketch a possible graph based on the following characteristics. What can you conclude about the equation of the function with these characteristics? So our first one is the range. So it says the range y is going to have to be less than 3. Once it says y is less than 3, I know that I'm looking at a parabola and not a linear function and not a cubic function. It's definitely going to be a quadratic function. So y is less than or equal to 3. And I know that there's going to be the y-intercept at -1. That's all the information they give me. So if I'm going to graph this thing, I just have to make a graph where y is going to be less than 3 everywhere. So if this is a height of 3, I know my graph is going to have a maximum point here. And y-intercept is at -1, so somewhere down here. So my graph is going to look something like this. Now, as long as my graph goes through a range of everything less than or equal to 3, and that y-intercept is -1, I'm good to go. So this parabola could shift left to right. It definitely can't change the direction of opening, though, because if I change the direction of opening, that means that y is going to have to be greater than a value, and that's not the case here. So what we can conclude about the equation of the function is that it has a leading coefficient that's negative, and it also is a quadratic function. So we had to make some assumptions, and that's just based on this information here. Our second example says that the range is anything whatsoever, so YER. So now we know we can narrow it down right away. We know this is either going to be linear or this is going to be cubic. And there's turning points, and there's 2 turning points in quadrant 2 and quadrant 1. Well, that just means we know now that it can't be linear, because linear functions have no turning points. So we're looking at a cubic function. So there's my roughly drawn quadrants. I have a turning point in 2 and 1. And so that means there's to be a turning point here and a turning point here, and YER is the only other information they gave me. So my function is going to look something like this and there. So we've got a turning point here in quadrant 2 and a turning point in quadrant 1. Now what I've assumed here is that the leading coefficient is positive. And that is a cubic function, we know that. Now the other thing is that I guess we all know that there's only one x-intercept as well. If I change this to make a leading coefficient that's negative, I can still come to the same, I can still draw a graph of that. So it would look something like this, where it goes down and then up and then back down again. So this would be a negative leading coefficient, and we still have one x-intercept. So in summary, depending on the type of function, whether it's linear, quadratic, or cubic, you can determine the following characteristics just by looking at the equation of the function. The possible number of x-intercepts, our end behavior. We can look at the possible number of turning points, the domain, and the range of the function. Now, if you want to take a look at that end behavior part, you need to look at the leading coefficient. So that's the number in front of your highest degree, your highest exponent, so like negative 3x squared. That's your leading coefficient is negative 3. And the degree of the function. So if it's a 2, it's quadratic. If it's a 3, it's cubic. And if there isn't an exponent, that's a linear function. And you can determine the end behavior of the function. So that's where it's going to start and where it's going to finish. So your assignment is on pages 393 to 397. Good luck, and we'll see you in class.